of you. Today we are going to start the third unit, Transient Analysis. Till now we have completed the first unit, that is basic concepts, and second unit, that is the circuit theorems. In the basic concepts, basically or mainly or importantly, we have seen the Kirchhoff's laws. We are having two laws. Number one is KCL and the second is KVL. KCL is nothing but Kirchhoff's current law. KVL is nothing but the Kirchhoff's voltage law. Friends, in the second unit, while solving the circuits, while getting the output or current or voltage, we applied KCL and KVL in the circuit. So can I say, for any circuit, we are using the application of Kirchhoff's law. It means we are using KCL and KVL. We can't solve the circuit without KCL and KVL. So, as I told you in the very first class, the Kirchhoff's laws are the analytical tools to solve the circuit. To solve the circuit means to get the current or voltage in any branch or element of the circuit. In the second unit, we have seen the circuit theorems also. Why we are using the circuit theorems? In the basic concepts, we have done some problems, and in those problems, we have seen the original network. We apply the KCL and KVL in that original network and get the output, means current and voltage. Is it okay? But in the second unit, while solving the circuit with the help of theorems, first we simplify the circuit. If the original circuit is this, first we simplify the circuit theorems, then we apply the KCL and KVL to this circuit, and then to get the output, means current and voltage. So this is all about these two units, basic concepts and the circuit theorems. Now come to the transient analysis. What is the transient analysis? The question is like this. So friends, I am taking an example for you, the physical example. Let's take a fan. To the fan we are applying the electrical current, right? And due to that electrical current, the fan is rotating and circulating the air. The circulating air we are getting. It means we are converting the electrical energy into the mechanical energy. Is it okay? So, what is this transient analysis in the circuit then? See, if this is the circuit, we are applying the input and getting output from it, right? So, in between input and output, applying the input, getting the output. In this process, this is nothing but the system analysis, right? The behavior of system is nothing but the system analysis. But this system analysis is having two types. One is transient analysis, second one is a steady state analysis. Transient analysis means, suppose we are considering a system. Let's take a diagram over here. Give me a minute, please. Suppose this is the system, you are having the system. Here I am taking it circuit because we are dealing in the electrical circuits. If I am dealing with the signal and system, I'll use the system. Is it okay? Now, I am applying some input to it, and I am getting some outputs from it. Now, the relation between input and output for this particular circuit is given over here by this graph. Is it okay? Let me change the pen color so it will be easy to understand for you. This is the graph of the circuit. This is the graph of the circuit. Okay. This is the output stage. This is the input stage. Right? Okay. Or you can say this is the time. The input we are applying with respect to time. Is it okay? The max output is 1, suppose. Is it okay? So, see friends, while applying the input to the circuit, we are getting the output, and the relation between output and input is given by this graph over here. So in this graph, if you will observe it carefully, we will see two types of situation we have. From 0 up to here, we are getting this variable kind of relation between input and output. Means input is increasing, the output is increasing. But after some time, at a certain point, it's become constant. Is it okay? So, up to here, this, right? This is the output. So, nearly at the output, but not exact. But not exact. The relation of the system is given by this graph. So, this behavior of the circuit is nothing but the transient behavior. Or I can say the system, the circuit is working in the transient region. Transient region means input is going to the output. Means we have to get, suppose for a particular system we have to get the input. We are giving some input and we are getting output 1. But we are not getting it at a sudden. Means we are applying the input and suddenly we are getting the 1. It's taking some time, right? Nanosecond and something. So in between them, that analysis is nothing but the transient analysis. Okay. So see, for this example, if 1 is our output, so 0.98888 up to here, 0 to 0.98 here, the behavior of the system is transient behavior. Transient behavior. Okay. And 0.98 to 1, actually it doesn't go exact 1, it will be 0.999999. Okay. So this 0.98 to this is like a constant, very constant term. So this is nothing but the steady state. This is nothing but the steady state behavior or steady state of the circuit or system. Are you getting? So this is nothing but the, so you can see here the transient behavior of the circuit is changing with the time, but the steady state is constant, no matter what the time is. At the steady state, the behavior of the circuit is like constant. Is it okay? I think it's very clear to you. So what is the transient analysis? You can easily understand now. So the total output of the circuit will be, if I talk about the output, so this output will be transient, output of transient plus output of steady state. Is it okay? The output total time, total output is transient plus steady state. Okay. Come to the transient analysis now. Introduction to transient analysis. See friends, the transient in the system is because of the presence of energy storing elements called the inductors and capacitors. Please try to focus on these two words, and these are inductors and capacitors. Is it okay? The transient analysis we are getting in the system because of the inductors and capacitors. Since the energy stored in a memory element can't change instantaneously, that is within the zero time. Is it okay? Inductor and capacitor elements will oppose sudden change in the system. We'll discuss later and in wide way, right? When the network consider only resistors, memoryless, no transient in the system at the time of switching. Suppose in the circuit we are having the resistance, there is a no transient in the circuit. We are applying V, we are getting I over here. But if in the circuit we are having the memory element, or I can say the energy storing devices or elements like capacitor and inductor, so they contribute the transient nature in the circuit. I hope this is clear to you. Now, the transient effect is more severe for DC as compared to AC. In the DC, the transient is more compared to AC. Okay, we'll see it how and why. Come to the transient. The concept of this whole transient analysis depends on energy storing element. So let's first understand what is these two elements. Alright. See, unlike resistors which dissipate energy, as I told you, resistor, if you are having a resistor, it consumes the energy. Is it okay? Current will come, it will dissipate the energy in the form of heat and something. So the resistor dissipate the energy. Is it okay? But unlike the resistor which dissipate the energy, capacitor and inductor do not dissipate but store the energy. What is the application of capacitor and inductor? The capacitor and inductors are the energy storing devices. Is it okay? So see, this is the capacitor given over here. This is the two plate parallel plate capacitor. Here on one plate we are having the positive charges, and on the another parallel plate we are having the negative charge particles. So it constitutes one electrostatic energy over here, okay, or electrostatic voltage over here, right? So this is nothing but the capacitor. We'll see in detail. So the capacitor stores charge, and the amount of charge stored on the capacitor is directly proportional to the voltage across the capacitor. It means if voltage will be high, the stored charge will be obviously high, right? Now, so the constant of the proportionality is the capacitance of the capacitor. We have seen in the last unit, I think in the first unit we have discussed little bit about the capacitor. The capacitor C, see, this is the capacitance. Capacitance is the, see, this is the quality, or I can say the capacitance is nothing but the ability of these two plates to store the charges. So this capacitance is directly proportional to the area of the plates and inversely proportional to the distance between plates. And here this is the capacitor constant permittivity, right? C equal to epsilon A by D. And the unit of C is nothing but Farad, okay, or Farad I can say. Now come to the formula now. Q equal to, this Q is proportional to the V. If voltage will be high, the Q will be high. Is it okay? Charge will be high. See, you are taking this structure, right? You are applying some output over here. If your output value V is high, so obviously the number of charge particles over here is very high. So Q is the charge, is proportional to the V. When I'll remove this proportionality sign, I'm getting Q equal to CV. So Q equal to CV, where Q is the time dependent quantity, voltage is also the time dependent quantity. Here the C is nothing but the capacitance, okay. So what is the voltage and current relationship of the capacitor? See, now we'll see by the Ohm's law, the relation between resistor and resistive current is simply we have seen. If this is V, if this is R, we applied V over here. So we are getting V equal to Ri. This is the current and voltage relation for resistor. But what about the capacitor? See, for the capacitor also we can check. The Qt is nothing but CVT. What is the current? Current is nothing but dq by dt. Is it okay? So to make this term current, can I differentiate both the sides like this? Yes, I can. So this will become current IT. Why? Because dqt by dt is nothing but the current. So this term become IT. What about this? The C is the constant, will come out. D by dt of VT. So this is the voltage and current relation between current and voltage relation for capacitor. So this is the formula. ICT is nothing but C dVc by dt. Here suppose someone will ask you what is the VCT. So we have to integrate it, right? So it will be like, the relation is ICT is nothing but C d by dt of Vt. Now I have to integrate this, right? So take it this side, dt equal to C dVt. Integrate both the sides. Is it okay? So this is d now. So this d and this integration will cancel out. So here I'll getting Vt, and this is integration of Ict dt. This c you can take over here like this. So Vt is nothing but 1 by c. Here 1 by c t naught to t. Here I'll take minus infinity to t. T is the at present time, minus infinity is the initial time. Is it okay? So this point is very important for the capacitor. A capacitor acts as an open circuit when connected to the DC voltage source. Okay, a capacitor impedes the abrupt change of the voltage. What it means? See, they are saying the capacitor acts as an open circuit when connected to the DC source. Okay, see friends, actually suppose you are having a resistor R. So the resistor is given by R. Resistance of the circuit is given by this. But if you are having capacitor, so what is the resistor of capacitor? This is also an electrical element, right? So this will be having its own resistance. So for the capacitors and inductors, we don't call the resistance, we call the reactance. Reactance is nothing but the resistor of this. So obviously the unit will be ohm. It means what I am saying to you, I am saying for the capacitor and inductors, we don't have the resistor. We have the resistor, but the name is reactance. Is it okay? So if you are having the capacitance, you can say this is the capacitive reactance. If you are having inductor, you can say it's inductive reactance. Is it okay? So the capacitive, wait a minute. So the capacitive reactance represented by Xc, and this is nothing but J by omega c. Is it okay? The Xc is given by J by omega c. This is the reactance. Now, for the DC, what is the omega value? 0. Frequency is 0, omega is 0. So if omega is 0, Xc is infinity by this formula. What is the mean by infinity? Infinity resistance means open circuit. Between A and B, if the circuit is open, so I can say here the resistance is infinity, right? No current can pass over here. Why? Because the resistance is infinity. So we'll discuss this formula later in the chapter, right? So the instantaneous power absorbed by the capacitor is given by this. See, what is the power? Tell me. In the first unit we have seen the power. Power is nothing but I into V. Power is also a time dependent quantity. So can I take IT into V of t? Can I take? Yes. For the capacitor, what is the IT? We have seen IT is nothing but Vt into Vt over here. Is it okay for you? Now, so this is nothing but the Pt for this. Correct. Now come to the point. Series and parallel capacitors, or combination of capacitors. See friends, for the resistance, we have seen the series combination and parallel combination also for the resistances. And if you will recall this concept, so I can write, see, for this the resultant will be R1 plus R2. Is it okay? And for this the resultant will be R1 R2 divided by R1 plus R2. Is it okay? Similarly, we have the formulas for series and parallel combination of capacitors. If capacitors are connected in series, so equivalent capacitance is given by C equivalent is nothing but 1 by C1 plus 1 by C2 plus 1 by C3 plus so on. Okay, it's like parallel connected resistors, because for the parallel connected resistors the formula is same, R1 plus R2 plus R3. So you can easily remember by correlating these two in your mind, whatever way you remember. Now come to the parallel combination. If those capacitors are connected parallel, so the equivalent capacitance is given by C1 plus C2 plus C3 plus Cn. As we have seen, the R equivalent is nothing but R1 plus R2 plus R3 plus so on. But here the same thing is given for the parallel connected capacitors, right? So again you can correlate these two terms and you can remember this formula very easily. Now come to the inductors. What are the inductors actually? An inductor is typically a coil of conducting wire. Means you are taking a coil of conducting wire. This is the wire, okay, conducting wire. This wire has its own resistance. But now this wire become inductor. So the resistance of inductor will consider the inductive reactance XL, denoted by XL. Inductive reactance, and this inductive reactance is given by J omega L. Is it okay? J omega L. So here the current will flow. I am taking IL. This is the time dependent quantity. This is the L, inductance of the inductor, and across this we are having VLT. Now again we will see here what is the relation between this, right? So if current passes through an inductor, the voltage across the inductor is directly proportional to the time rate of change of the current. See what he is saying. He is saying that the voltage across the inductor is nothing but L dit by dt. Is it okay to you? Now wait a minute. So how this formula came actually? See, we have seen in the capacitor Q is equal to CV. Okay. For the resistor we have seen V equal to Ri. Now for the inductor the phi is nothing but Li. The phi is the flux linked with the coil. Okay. So when you will differentiate this equation, you will get d phi by dt is nothing but L di by dt, and d phi by dt is nothing but the EMF introduced or produced. So this is nothing but produced EMF. So this is Vt is nothing but L di by dt. So this is the simple formula, or I can say the relation between current and voltage as far as the inductor is concerned. Okay, come to the next now. So if we have seen the formula for Vt is L di by dt. Is it okay? So what is the it over here? It is nothing but this L will come down, and this is nothing but Vt dt, right? And this time will be from minus infinity to present time. I hope this one is also clear to you. Now please try to understand this note point. An inductor acts like a short circuit to DC current. Why? The DC current means frequency is 0, no frequency, right? And we have seen the inductive reactance is J omega L. Omega is nothing but 0 over here. See, omega is nothing but 2 pi f. F is 0, omega is 0. So this is 0. What is the mean by 0? 0 means you short circuited 2 points. If A and B are 2 points, you shorted means the R equal to 0. And if you open two points A and B, it means R between them is infinity. I hope this is clear to you people, right? So the inductor acts like a short circuit for DC current, and the capacitor acts like a like an open circuit for the current. Okay. Now come to the formula of power. Power is nothing but V into I, again L DIL by dt into ILT. I hope this is very clear to you, right? Now come to the stored energy. This is the very important part. Stored energy in the capacitor. The total stored energy in the capacitor. Now, what is the energy? Energy is nothing but P into T actually. Power with time, power multiplied with time is nothing but the energy. Power, I can say the rate change of energy is nothing but power. That's the definition of power. The rate change of energy is nothing but the power. Okay. The expenditure of energy per unit time is nothing but power of particular system. Is it okay? So here the power is, the energy is, see, this is given for the small energy, like del E is nothing but P dt. For the very small time the energy given is like this. But I'm interested to get out the overall energy of the circuit. So the overall energy represented by E, so I'll integrate it like this. And time is nothing but from minus infinity or initial time to present time. Is it okay? So this is nothing but your energy. So here the energy is nothing but P tau d tau. Now P tau d tau is already we calculated, the power we already calculated actually for the capacitor over here. I'll show you. Wait a minute. So see, for the capacitor, here is the power. This is the inductor. Where is the capacitor? This is the capacitor. For the capacitor, the power was given over here. PCT is nothing but C dVc by dt into VCT. Now, the energy is, the whole energy is integration minus infinity to T Pt into dt. Here the Pt is, here is the Pt, C dVct by dt into VCT into dt. Is it okay? Like this. This dt will cancel out this dt. Now your reduced circuit is now, the reduced integration is CVT of dVt. Means we can integrate this Vt with respect to dVt. So it will be, and this is nothing but the energy. Is it okay? So this thing will be C V square like this. As you people know, the x dx is nothing but x upon 1 plus 1. X, this is x square by 2 plus c. This is nothing but integration of x. Here the similarly, instead of x we are having Vt, instead of dx we are having dVt. We have to differentiate the Vt with respect to dVt, or with respect to Vt only. So that's why your equation is C V square by 2. So half CV square. This is nothing but the energy stored in the capacitor. See over here the same formula is given for energy stored. This is the formula. Half CV square. Half CV square. This is the energy stored in the capacitor at any instant. If I am considering T, means this is the energy in the capacitor at any instant. Similarly, the total energy stored in the inductor is given by, the formula is same, the entire energy is integration of minus infinity to infinity, PL tau into d tau. Here again I am putting the value of power. We have seen the power in the inductor. Here is the inductor power. This inductor power, see, again I am calculating for you. The energy is nothing but minus infinity to T Pt dt. Is it okay? So minus infinity into t. What is the pt? Pt is L dit by dt into it into dt. Over here dt will cancel to dt. Now the equation is like dit of Lit into dit minus infinity to infinity. Again this equation the situation is same, like here this is x, this is dx. Is it okay? So this is nothing but Li I square by 2. This is the time dependent. So here you can see the formula is given half Li square. So here in the case of inductor the energy is Li square. If t is the time dependent, I is the time dependent, then this energy is given at any instant of the time. Is it okay to you? Now come to the series and parallel combination of inductors. So this is the series connection of the inductors. See, this is similar to the series combination of resistances R1, R2, R3. The resultant or R equivalent I can say is nothing but R1 plus R2 plus R3. Similarly, in the case of inductors, suppose you are having series connected inductors in the circuit, so the resultant inductance is given by the summation of all those inductors. Now come to the parallel combination. This is nothing but the parallel combination. Starting point, ending point, both are same. This is the parallel combination. In the parallel combination, the formula is given by 1 by L equivalent is nothing but 1 by L1 plus 1 by L2 plus 1 by Ln. I hope this one is also clear to you. Again, I'm telling you one thing. Mostly people, what they'll do, suppose in the circuit, two resistances are connected, 8 ohm, 10 ohm, and in between them, 3 ohm is connected. So by mistake, some people will take this 8 and 10, they are connected in series. Are they connected in series? No, they are not connected in series. Why? Because in between them another branch is connected. If suppose this 3 ohm is not, this 3 ohm resistance is not here, then I can say 8 ohm and 10 ohm, they are connected in series combination. But at this moment, I can't say they are not connected in series, neither in parallel. Is it okay? So don't do these mistakes, because mostly people do this mistake in the exam. Okay. Come to the example now. Find the current through 5 Henry inductor if the voltage across it is given, and also find the energy stored at t equal to 5 seconds. As we know, the energy at any instant in the inductor is nothing but half Lit square. Is it okay? Right? So he has given the time t equal to 5 seconds. So at t equal to 5 seconds we have to calculate. Means we require the value of it at t equal to 5 seconds. So what are the parameters given in the circuit? They have given. They are asking for the current. They have given the voltage. Is it okay? For the t less than 0, the voltage is 0. But as the t greater than 0, the voltage is now Vt. The voltage Vt is nothing but 30t square. Do you remember that formula? That Vt is nothing but L dit by dt. L di by dt. This is the relation, current and voltage relation for the inductor. So Vt is nothing but L di by dt. Right? And this is given for t greater than 0, because for the t less than 0, the condition given is the Vt for the inductor is L dit by dt. Is it okay? V is nothing but L di by dt. For the inductor, we have seen over here. See, I'll see you this. See, this is the relation. V is nothing but L di by dt. Right? Now, come to the question. The question is, we have to find out the it. We have to find out the it and Vt is given. So what is the It over here? The It is, we have to integrate 1 by L minus infinity to t, if you remember, Vt dt. This is nothing but the formula for the current in the inductor, right? It is nothing but 1 by L minus infinity to t and dt. Is it okay? Now see, this limits I can convert in two parts. I can divide into two parts, minus infinity to 0 Vt dt plus 0 to t Vt and dt. Is it okay? Now see friends, for this particular thing the Vt is 0. Why? Because Vt is given 0 for less than 0. For this integration, the limit of t is less than 0, because minus infinity to, this is the timeline. This is t equal to 0. This is t equal to minus infinity. And this is t equal to plus infinity. So minus infinity to 0. The given voltage Vt is 0. So this entire term becomes 0. So finally you are having 1 by L 0 to t Vt and dt. Tell me, is there any problem? So 1 by L. What is the L given over here? This is the 5 Henry. 0 to t. And where is the Vt? Vt is given 30 t square in this range. 30 t square multiply with dt. Right? This 30 will come, here I am taking, this 30 will come out, divide by 5, 0 to t square dt. The integration of t square is nothing but, this is 6 will, 30 by 5 will 6, and this is t cube by 3. So this is nothing but 2t cube finally. Is it okay? Now the current is 2t cube. Let me write it again. The current It is 2t cube. Is it okay? This is the current now. Now you can find out the energy stored. The energy stored Et is 1 by L. Wait. This is L by 2 It square. Right? L is given 5, divide by 2. It is nothing but 2t cube square. So this is 2.5 into 4 into t to the power 6. So this is nothing but 10 into t to the power 6. What is the t? 5 second. This is the 5 second. And it's 6. So when you calculate this, you will get 156.25 kilojoule. Is it okay? This is nothing but my energy. I hope this is clear to you. When you will calculate this, it will be 156.250. Okay? So this is all about this. So you can see how we can use the voltage and current relation for inductor and capacitor. We have to simply remember, again I am writing for you, Vt is nothing but L dit by dt. This is for the inductor. This is for inductor. For capacitor, the same thing is with ICT. ICT is nothing but C dVct by dt. This is for capacitor. Now if you are wish to calculate Vct and It, easily you can calculate it by integrating to this side. I hope the concept is clear for you. And for the inductor, the energy, instantaneous energy is given by half Li square. For the capacitor, it's given by half Cv square. Is it? The inductor deals with the current. So take the inductor L, inductance, and multiply with I square. The capacitor deals with voltage, so multiply capacitance with V square. Okay. In any way you can remember it, because we need this formula immediately should come to your mind. Okay, they can ask energy into the stored energy into the capacitor or inductor, right? Come to the second one. Consider the circuit in the figure under DC condition. What is the mean by DC condition? DC condition means the frequency is 0, means omega is 0. For the DC, the inductor is become short circuit. The capacitor is become open circuit. Is it okay? This is nothing but the DC condition. So they are saying in the DC condition, find. The question is I, VC and IL. Where is the I? Here is the I. Where is the VC? Here is the VC. Where is the IL? Here is the IL. Is it okay? And then the energy stored in the capacitor and the inductor. This is the good question. I'll take on the phrase page. The given circuit is 1 ohm, 5 ohm, 4 ohm, and this is the capacitor, and this is connected to 12 volt. Okay, fine. And this one is inductor given over here, 2 Henry. The capacitor value is given something, and this is nothing but the VC over here. And let me change the pen color first. This is the VC, this is the current I, this is the current IL. Now our question is, what is the I, what is the IL, what is the VC? And for the DC condition they are saying, complete DC condition. As I told you, for the DC, what is the nature of capacitor? Capacitor is open circuit for the DC. Why? Because we have seen the capacitive reactance XC is nothing but 1 by j omega c. Is it okay? So if this omega is 0, so it will become here, over here, infinity. Infinity means open circuit. For the inductor, for the DC situation, inductor behaves short circuit. Okay, why? Because the inductive reactance XL is nothing but j omega L. This is 0 ohm. This is infinity ohm. I hope this is pretty clear to you. So if we are applying the DC condition for this circuit, so this inductor in the circuit, I can open it. Can I? No, because inductor will be short and the capacitor will be open. Is it okay? Okay. And I'm going to do that thing. This I'll short. Okay. And this I'll open. Okay, fine. This is short circuit. This is open circuit. Fine. Now the question is find I, IL and VC. What is this? We have to find IC, we have to find VC, sorry. Okay. So now your circuit is like 1, 5 short circuited, like this. This is 12 and this is open branch, and this is the like this. So this is 1, this is 5, and this is the current in the circuit, and that current is nothing but IL. Over here I. Is it okay? So in the DC condition, this I will go to this side because this is the open branch. No current will come to this side. So this IL I can say, or I, both will be equal and will be 12 by 6, 2 ampere. Is it clear to you? It's 2 ampere over here, and the answer for IL is 2 ampere. The answer for this is 2 ampere in the DC condition. Now come to the VC. What is the VC? Well, friends, some people will say here the circuit is open, VC is 0. VC is 0. Without any calculation, they will directly write VC is 0. Why VC is 0? VC can't be 0 because the 2 points are open. Open means there exists one voltage over here. Right? If they are short circuited, then I can say this is the VC equal to 0. But the points are open. It means absolutely we have the voltage over there between 2 points. Right? So I can calculate, I can apply the KVL in this mesh. In this mesh I will apply the KVL. I will start with the 12. At the end I am getting 12. Okay, fine. Here drop will be there, minus 2 into 1. 2 into 1. Why? What is 2? 2 is the calculated current in the circuit. So voltage drop is 2 into 1. Now come to this side. Is there any current in 4? No current. So 4 into 0. Here I am getting plus minus. So minus VC. I am coming again and reaching to 12 is equal to 0. Right. So the situation is like now. The 12 minus 2 minus 0 minus VC equal to 0. So VC is nothing but 10 volt. Is it okay? So the answer for VC is nothing but 10 volt. Is it fine to you? Now, the next one, they are asking for the energy also. So energy in the inductor is nothing but half Li square. Energy in the capacitor is nothing but half CV square. I think you can easily determine this. How? Because you have the value of I, that is 2 ampere. You have the value of V, that is 10 volt. So easily you calculate the energy over here. Is it clear to you? I hope. So for this circuit, we calculated the I, VC and IL, and energy stored in the elements. Okay. This is nothing but 2 ampere. This is nothing but 2 ampere. And this is nothing but 10 volt. So the energy in the inductor is nothing but half Li square, half 2, because L is given is 2 Henry here, and this is 2 square. So finally this is 4, this energy stored is 4 joule. Is it okay? Now come to the VC now. The energy is nothing but half CV square. The energy stored in the capacitor. 1 by 2 into 1 Faraday into, what is the V? V you calculated. So this is nothing but 50 joule. Is it okay to you? So this is all about these two problems. Okay. Now come to the important characteristics of the basic elements. The VI relation. For the resistor, V equal to IR or V equal to RI. But for the capacitor, the V is nothing but 1 by C. We remember this formula, right? And this formula we can get by this. V equal to L di by dt. For the inductor, sorry. This is for the inductor, this is for the capacitor. For the capacitor, the VI characteristic is, so V equal to 1 by C integration I dt. Okay, and this is the initial voltage. Okay, or you can take here minus infinity to t. For the inductor, V equal to L di by dt. Now come to the IV relation. Here I'll take I this side and another this V by R I'll take to this side. For the capacitor, I is nothing but C dV by dt, and for the inductor it's like this. What about the power? The power is the P equal to I square R and V square by R. We have seen this. For this, the power is, for the capacitor, the power is half CV square. For the inductor, the power is half Li square. Is it clear to you? The series combination of the resistors. The series combination of the resistors are R1, R2, R3, R4. Similarly, the inductor has the same formula. L equivalent is nothing but L1 plus L2 plus L3 if inductors are connected in series. But for the capacitor, the formula is, this is given for 2 only, means 2 capacitors, C1, C2 by C1 by C1 plus C2. Is it okay? Or the main fundamental formula is C equivalent is nothing but 1 by C1 plus 1 by C2. Is it clear to you? Come to the parallel now. For the parallel circuit, the R equivalent is R1 R2 by R1 plus R2. L equivalent is nothing but L1 plus L2 divided by L1 L2 divided by L1 plus L2. Okay. For the DC, the resistance is same. Whatever resistance is given in the circuit will be same. But for the capacitor, in the DC condition, it behaves like open circuit, and the inductor behaves like short circuit. Is it clear to you? Now, circuit variable that can't change abruptly. The circuit variable C. For the resistance, there is no such thing applicable. But for the capacitor, the voltage is not changed abruptly. What it means actually? This is the base for the transient analysis or initial condition, whatever we are going to learn. See, the property of capacitor is, suppose this capacitor stored 5 volt. Suppose this capacitor stored 5 volt. Now you are applying something else to this capacitor from the outer 10 volt. So it will oppose the change in voltage. Right? It means I can say the 5 volt is not abruptly changed over the capacitor. This is the property of capacitor. In the capacitor, the voltage is not changed instantly. Okay, it takes some time. That is nothing but property of capacitor. And for the inductor, the current is not changed instantly, or the current can't change abruptly. See. So this inductor opposes the change in the current, capacitor opposes the change in voltage value, and this phenomena, this concept is the base or reference for the entire unit. Okay, is it clear to you? So from the next class onwards, we'll solve some circuits, some problems based on this capacitor and inductor formulas, the formulas of voltage and current for the capacitor and inductors. In the next slide or in the next video lecture, we'll start the initial condition or transient behavior of the circuit. Okay, friends. So again, I'm telling you, do problems, and you can refer the book Alexander and Sudoku for that. Okay. So we'll meet in the next class. Till then, take care and bye.